All right, let's talk about something huge. We're going to tackle one of the absolute bedrock rules of the entire cosmos, a law so strict it controls everything from the way a candle flickers to how a star explodes. We are talking about the law of conservation of energy.
But let's just start with a question that sounds super simple, but trust me, it goes deep. Does energy actually disappear? Or, are our own eyes just playing tricks on us?
I mean, think about it. We see what looks like energy disappearing all the time. You give a ball a good push, it's got motion, it's got energy, and then it just slows down and stops. The energy of motion is just poof, gone.
Or, hey, what about a candle? That little flame is just pumping out light and heat. That's pure energy right there. But after a while, it gutters and dies out. The energy factory just shuts down. And come on, in our world, this is a daily struggle. A fully charged phone battery is this little powerhouse of potential, but as you use it, that energy just drains away to nothing. In every single one of these cases, it feels like the energy was used up, just destroyed.
So, this is our mission. We're going to put on our detective hats and solve the mystery of this supposedly missing energy. For real, where does it all actually go?
Okay, our first stop on this investigation takes us back to the world of classical physics. Think Isaac Newton. Guys who saw the universe as this giant, predictable clockwork machine. And the very first clues they found came from just watching things move.
First, they put a name to something called kinetic energy. And the idea is really straightforward. It's the energy something has simply because it's moving. A rolling ball, a falling apple, a whole planet zipping through space, if it's moving, it has kinetic energy.
But they quickly realized that wasn't the whole story. There was another kind of energy. Potential energy. This is stored up energy. Energy that an object has just waiting to be unleashed because of where it is or what state it's in. Think about a drawn bowstring or a wrecking ball held way up high. It has the potential to do some serious work.
And this is where it gets really cool. Watching how these two play together. When you toss this tomato into the air, its speed, its kinetic energy goes down as it climbs. But the higher it gets, the more potential energy it's storing up. At the very peak of its flight, it stops for a split second, holding maximum potential energy. And then as it falls, all that stored up potential gets converted right back into the kinetic energy of motion. See, it's not a loss, it's a trade-off. Now this idea of a trade-off, this concept of transformation, that was the big clue. And it led directly to the next huge breakthrough, the first law of thermodynamics. This is where our detective story really starts to heat up, literally.
So let's meet our lead investigator, a guy named James Prescott Joule. Now, back in his day, the popular idea was this thing called the caloric theory, that heat was some kind of invisible fluid that just flowed around. But Joule, he wasn't buying it. He had a hunch that the lost energy from things like friction wasn't really lost at all.
So he built this absolutely ingenious experiment. He used a falling weight, that's mechanical energy, to turn a little paddle inside a sealed barrel of water. The paddle churning through the water created friction, and that friction warmed the water up. And Joule was meticulous. He measured everything down to the tiniest degree and proved that a specific amount of mechanical work always created the exact same amount of heat. That lost energy from our rolling ball, it wasn't gone. It was turning into heat through friction. And the conclusion he reached was an absolute game changer. Energy is never, ever lost. It just changes its costume. It's a master of disguise. Mechanical work becomes heat. Chemical energy in a battery becomes electricity and light. The total amount in a closed system is always the same. But that just leads to a deeper question, right? Why? Why is this law so unbreakable? Well, to answer that, we have to go even deeper, into one of the most elegant and frankly beautiful ideas in all of physics, Noether's theorem. Our guide on this leg of the journey is the incredible German mathematician Emmy Noether. And if you're wondering just how brilliant she was, don't take my word for it. That quote you see is from Albert Einstein himself. She was the one who uncovered this profound, hidden connection between the symmetries of our universe and its most fundamental law. And this is the heart of her incredible idea. A symmetry in physics just means that if you change something, like your location or the time, the basic laws of physics don't change. Her insight was that for every single one of these symmetries, there is a physical quantity that has to be conserved. And here it is. This is the big reveal, so check this out. If the laws of physics are the same here as they are on the other side of the galaxy, that's a symmetry in space, then linear momentum is conserved. But now for the big one, the clue we've been searching for. The laws of physics are the same today as they were 1 billion years ago and as they will be 1 billion years from now. Because of this time symmetry, energy must be conserved. The law of conservation of energy isn't just some arbitrary rule. It's woven into the very fabric of reality because time itself is consistent. It's just mind-blowing.
But hey, no law in physics ever gets a free pass. Just when we think the case is closed, the 20th century rolls around, and a bunch of new theories show up that seem to poke some serious holes in this supposedly fundamental rule.
First up, of course, Einstein. His legendary equation, E=mc², didn't actually break the law of energy conservation. It just expanded it in this incredible way. It revealed that mass itself is just a ridiculously concentrated form of energy. So in things like nuclear reactions, you can convert mass into energy, but the total amount of mass energy is still conserved. The law just got an upgrade.
And then came the absolute weirdness of the quantum world. At the tiniest possible scales, it looks like particles can just pop into existence out of absolutely nothing, as long as they disappear again almost instantly. So does that violate the law? Well, physicists say no, thanks to something called the Heisenberg uncertainty principle. It basically allows the universe to take out these tiny, microscopic energy loans, as long as they get paid back incredibly fast.
But then, on the largest possible scale, there's another puzzle. We know the universe is expanding, and as it does, the light traveling from distant galaxies gets stretched out, and that process makes it lose energy. So where does that energy go? You know what? This is a question physicists are still actively debating, pushing the absolute boundaries of how and where this law applies.
So, after chasing all these clues, seeing all the transformations, and facing down all the modern challenges, what's the final verdict? What does this all really mean for the universe we live in?
It turns out this is about so much more than just physics. This law is the foundation of causality itself. You can't have an effect without some kind of energetic cause. It's the whole reason the universe seems predictable instead of just magical and chaotic. In short, the fact that energy is conserved means the universe plays by a consistent set of rules. It keeps the books, and that is what allows us to do science and understand it in the first place.
So here's the ultimate takeaway. The next time you see a ball roll to a stop or your phone battery dies, just remember that the energy isn't gone. Not at all. It was just transformed, probably into a tiny, imperceptible bit of heat. It's all still out there, because the universe runs a tight budget, and the accounts are always balanced. Energy is the ultimate currency, and in the end, the house never loses.